All right, so the other Brian's already warmed you up, so I'm just going to dive right in. If this will let me go. Cool. So very briefly, introduction to me. My name is also Brian, but he was here first, so I tend to be Brian S, and he tends to be Brian. For my day job, I work at ARM on fixed function pixel processing hardware, so I kind of live and breathe pixels, basically. I built this guy a couple of years back, but it didn't compete. And then this year, I entered Minnie Mouse in Pi Wars this year, which is the size of a mouse. And in here, I only have two sensors. So I have a camera and I have a compass, effectively. And I would say I was kind of inspired by Pyrodyne the year before, where Mark basically showed us that you can do everything with a camera. So why are we all messing around with dedicated sensors? And as you can imagine, I haven't got a lot of space in here, so I was quite happy to just put a camera in and nothing else. I used the camera for all of the autonomous challenges, and it went pretty well. So I had the fastest Hubble, and I was second and third in the maze and in the line following and the maze, respectively. And basically, I'm going to show you all of the algorithms I have in about 15 minutes. So they can't be that complicated, right? So I wanted to do this talk because I feel like people think that computer vision is this really crazy, complicated, scary voodoo stuff. And in my case, I'm running really, really simple code. And it was perfectly adequate for Pi Wars this year. So I want to try and show that it's not that complicated. And hopefully you don't all walk away being like, what the heck was he on about? But we'll see. So I'm going to first talk a little bit about the tools I had to help me develop Minnie Mouse, and then run through the specifics of all the algorithms. And obviously the audience is quite varied, but hopefully all of you can get at least something out of this. And it's worth saying that I have to gloss over loads of details. But if you do want to know more, I'll talk your ear off later. Just come and find me. As for the title of the talk, so I put computer vision in quotes because, in my opinion, what I'm doing is really on the basic end of what you might call computer vision. I don't want to insult anyone that works on like cutting edge stuff by saying that this is the best. And the from scratch part is because I actually didn't use OpenCV or anything like that. I wrote it all myself. It's not because I want to show off. It's because I use Go, and the OpenCV bindings for Go are really bad. But also that you can learn something that way. I only had a 0, so I wanted it to be quite fast. I wanted to be able to control it. And I want to try and show that you can do this yourself, basically. All right, so tools. If you're going to be doing computer vision, maybe it's obvious, but you really need photos of the problem that you're trying to solve. And I'll say I'm going to put all these slides up just after the talk, so if you want them, I can send them out. So they need to come from your robot's eye view, because like what you think a problem looks like from where you stand is very different from what your robot thinks a problem looks like. I really like this RPi CAM web interface thing. You can just install that on your Pi, and it runs a web server, and you just go to a web page, and you can capture images or videos from the camera. And you can do that really early on, before you've got any camera code at all, right? You can capture photos without having to write any code. You're going to need a way to prototype, so to hack things together and get a feel for the problem. I kind of recommend doing that on photos that you've captured, so you don't have to mess around with your robot, because it's probably not that stable early on in the development. Then later on, you're going to need testing. So you need to be able to drive your robot around, see what it sees, see what the algorithm thinks it sees, and be like, ooh, I wasn't expecting it to do that, and hopefully take a picture of that so that you can test and improve. And you might find that your code is too slow, in which case a profiler will help you make it faster. So here's some photos. The top ones, it says are from September, so I think at that time I'd just about got this moving. But I didn't have any code for the camera, and I used that web interface to just take photos of some stuff to see what it looked like. And then the bottom ones, they're from around Christmas time, when I did have some camera code, and they're captured from my robot code directly. And that's more or less what the robot's using when it's driving around. For prototyping, I spent a couple of evenings with Python and OpenCV. I wrote some code to detect white lines and detect the horizon. I just wanted to get a feel for the problems. What I came up with was not suitable at all for the competition. It took, like, I don't know, a third of a second on a powerful PC. But it did help me sort of understand what I was trying to do. Then, as the robot develops, it's really useful to have some testing tools. I've got two main tools for Minnie Mouse. So the one on the left, it runs live, it runs on my laptop, and it can connect to the robot over Wi-Fi, and I get the orientation of the robot and the camera view. So at any moment, I can press a button, and it will capture that camera view to a file. So if I see something that's interesting, I can just save it to a file and play with it later. And it also lets me run my algorithms on what the camera's actually seeing on my laptop instead of having to copy it to the robot every time. So that can sort of speed up your development a bit. And then the other tool is the one on the right, and that only runs on image files. So any pictures that I captured, I can load into that, and I can work on the algorithms by themselves without having to have the robot running, without having to have a course set up. So I'll just go down to Makespace at the weekends, take a whole bunch of photos of Brian's courses, and then go home and hack without needing them. And of course, in that one, I can also see how fast stuff is running. And so the last thing I mentioned is profiling. When you've written something, you might find that it's too slow, basically. What I will say before, as a sort of caveat, is premature optimization is the root of all evil, is this like famous quote. And all that means is don't spend any effort optimizing something until you know for a fact that it's too slow, because it's just wasted effort, basically. So in my case, it turned out it was too slow. And this here is output from the Go profiler. And basically what it shows you is every box there is a function, and the bigger and redder a box is, the slower that function is. So this one here, conT2ino pointer, really catchy name, is taking 46.5% of the time for this algorithm, which is finding the horizon. So I knew if I could somehow speed up that function or remove it entirely, my code would go twice as fast. And I would have no idea, because this isn't actually one of my functions. This is part of the core language. And so I was quite surprised to see this innocuous thing was actually taking half my time. So it's really useful to be able to actually see this, because sometimes it's hard to do it intuitively. And there's a note there, only make the slowest parts faster. If you've already got a bit that's really fast, there's no point in making it faster when this random pointer conversion is taking like 2.5 seconds. Okay, so that's it for tools. Hopefully you guys are still with me, and we can dive into some algorithms. I got a few different building blocks to talk through. The first one is thresholding. For all of this talk, basically, I'm going to consider a pixel as just one value between 0 and 255. Hopefully that's familiar to some of you. So if it's 0, it's black. If it's 255, it's white, and anything in between is grey. And thresholding is taking a grayscale image or a color image and converting it to just black and white. So you only have 2 pixel values. And the idea is you take all the darker pixels and make them black, and all the lighter pixels and make them white. And depending on the image that you put in to begin with, after the thresholding, black and white can mean something useful. So here, we've got quite a nice picture where it's a black cat, black kitten on a light background. So after I thresholded it, kind of handy, I made a cat detection algorithm, right? All of the white pixels are background and all of the black pixels are cat. That wasn't so hard. Like a cat detector should be much harder than that, surely. So this is kind of useful to help you throw away information. The first one is kind of complicated to decide where the cat is, but this one it's dead easy. Is it black or is it white? And I use this as a part of all of my other algorithms. So is it an edge or not? Is it a ball or not? That kind of stuff. And there's a link there to a blog post. Great example of wasting a weekend on premature optimization. What I thought would be fast was actually like 100 times slower than what I thought would be slow. Okay, so thresholding. Really, it's very simple. You go through each pixel in your image, and for some threshold, so I picked 128 here, which is in the middle of our pixel range. If it's greater than 128, we make it white, and if it's less, we make it black. And down here is the result. This is nearly black and white already, but there is some gray here. And after thresholding, it becomes a sharp black and white. So that's cool. But then the problem with saying anything greater than 128 is white is if your difference between black and white gets smaller, then you can get a situation like this. So towards the top of this image, the difference between the dark pixels and the bright pixels gets smaller, and so the whole of the top of the image gets white, and we can't find our line anymore. So we've got this problem where in some parts of the image, all of our pixels are above this threshold of 128. So, okay, one thing you could do is just shift this threshold to be here instead, and then it would work okay. The problem with doing that is that in other parts of the image, all of our pixels would then be below the threshold, and they'd just come out black. There's a bunch of different ways to solve this. The one I took is I went through each row in the image, and I adjusted the image so that the darkest pixel was black and the lightest pixel was white, just by sort of stretching the values. So this is a two-step process. First, you take the darkest pixel and you subtract its value from all of the pixels, and that effectively moves them all down to 0. And then after that, you stretch the rest of them out. And now I can use a threshold of 128 through the whole image, and it should come out fine. So in the code, it looks like this. For each row in the image, we find the darkest. Oh, sorry, I didn't mention this isn't any particular programming language. It's Python-ish, but it's just to give you an idea. So for each row in the image, we find the darkest, we find the brightest, and we find the difference between them. And the difference is important so that we know how much to stretch them afterwards. And then, for each pixel in the row, you do step 1. So you just subtract the darkest from the pixel. And then step 2 is this divide by the difference, and that will stretch everything out. And then, once that's done, you can threshold with 128 again. This here's the result. So the same input image we had before. This is after you've done all of this shifting and stretching. And you can see that at the top here, where there wasn't much contrast before, the background pixels are a lot darker than the line. And then this is after running it through with a fixed threshold of 128. And it's not perfect. We still have this little white bit creeping in here. But this ought to be good enough for a line finding thing to find the line. And this is the result on a real picture coming from the robot. And this is the line. So this thresholding algorithm is all of the image processing I did for the line following. Like, that's literally it, the 15 lines of code you've just seen. And that was enough to turn the camera into a simple line following sensor. The next thing I want to talk about is edge detection. So we normally want to find a thing in an image, right? And to find a thing, you need to know where the thing starts and where the thing ends. And basically that means finding edges. Hopefully most of you are familiar with Pi Wars, but we have this challenge where there's a square arena with colored boards in the 4 corners, and the idea is you have to find the colored board and visit them in order. So the goal of this part of the presentation is to find that colored board. All right, so if we want to find edges, first we need to know what's an edge. It's basically just a difference between pixels which are nearby to each other. What we need to decide is which pixels are we going to compare, how much difference does there need to be before there's an edge, and how exactly do we compare them. So where's my lasery thing gone? So here, that's definitely an edge, right? There's no real question there that between the black and white there's an edge. Here it's a bit less obvious. It's a bit hard to tell, is this an edge or is it just a gradient between light and dark lighting in the image? And of course, I've used black and white because it's simple, but it could also be color. Here we've got an edge between 2 different colors. I'm looking for this board, which has nice vertical sides. So let's have a look at a simple vertical edge detector. We're looking for differences between pixels, right? So let's just compare each pixel to the one immediately to its left. So if we take this pixel, it's black, or 0, and we compare it to the one next to it. So we subtract, this one is this one, and then we subtract the one from its left, and 0 minus 0 is 0. So far, so good. Here, we take the white one, it's 255. We've got a black one next to it, subtract 0, and you end up with 255. And as if like magic, what you end up in the output image is a nice bright white line here where the edge is and everywhere else is black. And that's all you need to detect a vertical edge. In code, it looks like this. So for each row in the image and each column in the image, we set the output pixel to 1 input pixel minus the input pixel next to it. you need this abs thing here, so that gets the absolute value, because if you did black minus white, you would end up with minus 255, and you need all positive numbers. So if you just stick an abs in there, then that solves that problem. You'll also notice here in the output we don't have any data. That's because when you're in this column, there are no pixels on the left to compare against, so you can't get any information for the first column of the image. So this is the edge we saw before. Because we're comparing pixels left and right, you won't detect any horizontal edges at all. So here there's a really strong horizontal edge, but because we're only comparing pixels sideways, they all come out black. Here we find 2 pixels of edge, one when it goes from black to white and one when it goes from white to black. And this is the one before that was a bit sort of questionable, and you can see we have got a lighter grey line here, but it's not super bright white because the edge in the input image is a bit more subtle. So if you apply that to a real image, you get this. It's already done a fairly good job, I would say. We've got greyish lines on the edges that we care about. And then maybe you can guess, we can apply that thresholding that we just talked about, and now we've got a much better image with white pixels where all the edges are and black pixels everywhere else. And of course, we were looking for vertical edges. If you want to find horizontal edges, you can just compare above and below instead of left and right, and all the horizontal ones come out. And this diagonal line here shows up in both, because diagonal lines have some horizontal bits and some vertical bits, right? That's what makes them diagonal. There's much better edge detection algorithms. So if you are playing with OpenCV or whatever, there's Canny Edge Detector, it's like the common one, which does some of the same stuff but does a lot of processing on it as well. I found this very simple, just literally compare pixels next to each other was enough for PyWars. So this is the last part of my OpenCV for the Hubble challenge, basically. We've already found edges, but we don't really want to know edges, we want to know lines, right? The thing we're looking for is a rectangle. A rectangle is made up of lines, so we need to turn our edges into lines. Finding curves and lines at angles is a bit harder, but if you're only looking for vertical and horizontal lines, it's dead simple, and that's kind of handy, right? Because I've only got vertical lines and horizontal lines here. Okay, so we've got edges. What does a line look like? Well, here's edges which are just texture on the floor, basically. This is a vertical line, and what it looks like is in the image, it looks like a vertical column containing lots of edges. So that's all we need to do. We need to find columns in the image which contain lots of edges. So there's a lot of ways to do this. I chose to just add up all of the pixels in the column and find the average, divide by the number of pixels. So if this was that edge detected image that we just looked at, and this would be the result of adding up all the columns. So here it's all black. So black plus black plus black divided by 3 is black. Here it's all white. So white plus white plus white divided by 3 is still white. And you can see as this line goes from perfectly vertical to less vertical, the brightness of the pixels after we've added them together and averaged them gets lower. And so we've made a vertical line detector, right? All of the bright pixels afterwards are vertical lines and everything else is not. So there's the result of running on a real image. It's this red square, red rectangle down at the bottom. This is just the average value for every single column in the image above. That's what it looks like a bit bigger. And you can already see a couple of problems here. So the left-hand edge of the board was showing up as 2 lines, one when it went from black to grey, I guess, and then from grey to red or something. And this is a problem because it makes the robot think that there's 2 lines when really there should only be 1. And then over on the right-hand side, the line wasn't quite vertical, and that means that instead of being one single bright spot in that image, it's spread out over a few columns. We can tweak the code a tiny bit to solve that. So instead of doing each column individually, we can combine together columns which are nearby to each other. So this is just combining adjacent columns, and that will have a sort of blurring effect on that, that stripe, so that all of our lines get spread out a bit. And so the really bright ones will get made darker, but the ones which are made up of lots of segments should get merged together. And again, perhaps you guessed, after you've done all of this averaging, you can threshold. So this was averages of just one column. This is merging some columns together. I forget how many. And this is after thresholding. And that's it, right? I got two really bright white spots corresponding to my two vertical lines in the image. So, mission accomplished. When that's done, I got those. They tell me where the board is. And it only took about 15 minutes to explain, so it can't be that bad. So, the steps, just to recap. First, you find edges in the image just by comparing pixels to each other. Then you apply the threshold to make the weak edges disappear and the strong edges get stronger. Then you look for lines in the image by bunching columns together. And then once again, we threshold so that we only keep the strongest two vertical lines and we throw everything else away. So, you know, there is a vertical line here, which was showing up. You can just about see it here. But after the thresholding, because it's not as strong as the other two, it gets dropped. So with those steps, you've got everything you need to build Hubble, basically. We turn to where we think a corner is. We run this algorithm. That gives us the two spots for where the board is. If you want to, you can use that to then center your robot a little bit. And then you simply sample the middle point between those two lines. If you have a good idea on where the board's going to be vertically, which you should do. For me, I literally just sampled the middle pixel vertically in between the two lines. That tells you the color, and then you can turn to the next corner and do it all again. So that's the technical content. Just want to try and draw some conclusions. Hopefully I didn't lose you all with my onslaught of diagrams. I want to say first and foremost, keep it simple. What I was trying to show today is that you can understand every single part of this process, right? All of the challenges for Pi-walls are fairly well defined, at least this year they were. Not that they're badly defined this year, but the courses last year were quite simple. So your code doesn't really need to worry much about what's in the background, right? Because it should be fairly plain. For Hubble, I could be fairly confident that if I was pointing at a corner, the two biggest vertical lines were going to be the edges of the board. And my code just assumes you're only going to see two lines, so don't bother trying to do anything fancier than that. If you can, use a very small number of pixels. This naturally blurs things, which is counterintuitively very useful. If there's a lot of detail in your image, then that shows up as speckles, and that can really confuse your algorithms. So if you go small, it naturally blurs. And of course, if you halve the width and the height, you reduce the number of pixels by 4, and that reduces the amount of work you have to do by 4. So my line follow is 32 by 32 pixels, and I only use black and white. My maze, 40 by 80. I think I am using color there. And the Hubble is 100 by 100. Not for any particularly good reason, but I wasn't running it all the time. I was only turning, taking a picture, and so it didn't matter so much about the number of pixels. And 3 is try and put some time into tools and testing. So it's much easier to develop and debug these things when you can actually see what the robot sees, see what the robot thinks it sees, and you haven't got to guess what went wrong when it suddenly turns a left and you weren't expecting it to. I know it's really hard to do when it's like crunch time and writing tools feels like you're not getting any closer to your goal, but I think it's worth trying to take some time out and spend it on that if you can. Right, and I think I have a couple of minutes left, so I thought, well, let's have a look at this year, because we don't have colored boards anymore. So I just took the code that we've just talked through and shamelessly stole some pictures from Twitter, because people keep posting pictures of barrels. So I got this one from Brian, and it does okay. I think I kind of got lucky, like the table here has a line there, which shows up here, and it just about lines up with the edge of the barrel. Which means we do end up with a signature here, and the right-hand side is detected okay. But otherwise, I think all of this, because I'm running on the whole image here, I think all of this would have confused it. But still, luckily, we got 2 lines. If you split your image into 3, at least this is how I think I would do it, and take an average of each segment in the image, then you can probably guess if it's not red or green, then it's probably background. If it's red, it's probably a red barrel, and it's not red or green, it's probably the background. A much better image with a nice bright white barrel on a nice pure black background. So here it works really great. And there's really no doubt that the edge detector has picked out the barrel, the line detector has picked out the edges. And again, if you just average these 3 segments, you know, black, probably background, it's a white barrel in this case, probably a barrel. and black for background. And then, of course, Mike had to go and ruin it by posting this one. And here, by far the strongest lines are the glare from the camera flash, basically. The difference between the white here and the green is much greater than the difference between the background and the barrel. You can also see how speckly this is because it's such a high resolution input image. I didn't try scaling it down, but I don't think it would have helped. So I suppose this shows you, write the algorithm for the actual challenge, don't try and repurpose your old one. And even lighting is very useful as well as testing. All right, and that's it. Thank you so much for listening. Do we have any time, or am I off?
Yeah, we have time for some questions, if there are any questions from the audience.
What does fixed function pixel processing do?
So CPUs run programs, right? You can write code, and they will do whatever the code says. GPUs also run programs. What I work on can't run any programs. So it has a bunch of hardware which does very specific operations on pixels, and you can control them. So there's like a matrix multiply, say. I can control what values are in the matrix, but I can't control the operation. So this is used, like the camera pipeline on the Pi is all fixed function. That means it's really, really fast at doing what it does, but you can't control it that much. Whereas the GPU, you can control it, but it's not quite as efficient. And the particular fixed function hardware that I work on runs the display output, basically. Sorry? Good.
Anyone else?
Yeah. What sort of frame rate did you get when you did that process?
Very fast, actually. I think, like the Horizon code for the maze, it was taking about 2 milliseconds, so the processing really wasn't the bottleneck there. I forget what frame rate I was grabbing from the camera. It was at the same speed as the control loop. It was either 30 or 60 frames a second, but none of the processing was heavy enough to slow that down in the end, because as I showed you, it must be like 30 lines in total for most of it.
You were taking pictures while it was rotating. Did you have to worry about rolling shutter?
Yeah, so I didn't do that. I have a compass on here, right? So I actually found if I turned what I thought was 45 degrees, the compass was really good, well, compass plus gyro plus accelerometer, and I was almost always just facing the corner. So I turned, stopped, took a picture, turned, stopped, took a picture. So at least for Hubble, I was never turning and taking photos at the same time. For the line, I never noticed it being a problem. I could see in my web feed that it was wiggling around a bit, but the algorithm seemed to cope. I didn't talk about how I took that black and white image and found a line, but yeah, it wasn't too complicated, and it didn't seem to care. But we can talk about that later if you want to know. Yeah, so for those I was stationary, which helps. I originally thought when I was driving towards the corners, I might use the camera to see where the board was to figure out how close I was. In the end, I just counted wheel rotations, and it's only like 60 centimeters, and that was perfectly adequate for me. Sorry, I feel like...
I think I can guess from what you were just saying that rather than moving it at times if there wasn't a board in the image.
True, yeah. So if that happened, then the edge detector would have looked for edges in the plane thing. It would have just found noise and speckles. Then it would have thresholded that, and then maybe it would have found some lines. But because the orientation sensor is very reliable, I didn't need that. I could always turn 45, and I could always spot the board. Of course, you can, if you don't want to do it that way, you can implement in your algorithm to detect and handle that case, but I didn't bother. Yeah, indeed. So with the stretching part of the thresholding, it won't go back. But with the stretching part, it's a divide, right? If you don't have a lot of difference in the image, then you divide by nearly 0, and then stuff goes crazy. You get lots of white bits all over the place, and that's how I would have checked if there was a board. If the stretch factor was too big, I would have ignored that frame. Yeah, I was.
So you got a third sense for that.
Yeah, you can dead reckon for sure, but you can do the same with DC motors and a sensor. So this one has DC motors with encoders, and it can also dead reckon okay. But I was only doing dead reckoning with straight lines, which is easy. As soon as you try, I tried to do arcs, I tried to get fancy and do arcs between the corners, but it just failed so badly because as soon as the wheels slip, you really have no idea where you are. But straight lines is fine.
When you found the time delays in the code, was that a specific piece of software you used?
Yeah, so it will depend on the language you're using. In Go, you just add some lines and it will do a profile and then you get a file. I can show you afterwards what it looks like. In Python, it's pretty similar. And actually, it will open in a web page and show you that view with all the boxes, and you can dig down into them and see which ones are slow. But yeah, I can show you it later if you want. The B&O 055. I didn't put any effort in whatsoever. I had a nightmare evening where I took some Python code and ported it to Go, and it didn't work. And I got out a logic analyzer and I compared the traces between the Python and the Go, and it was identical, but mine didn't work and theirs did. So I started from scratch, and I never had a problem. It doesn't work great for a long time. So if you drive around in circles for 10 minutes, it does drift. But come on, the Hubble took like 15 seconds. It wasn't drifting a lot in that time, basically. And the maze, yeah, it was okay. It was okay. Wasn't great, but it was okay. All right, I think I'm out of time.
Please join me again. Thank you very much.